All right, Remsen St. Mary's freshmen. Today we're going to begin our Unit 5 lecture. Today we're going to be starting with motion. Now, motion is going to have speed, velocity, and we're going to talk about acceleration within there. So remember our little engaging activity that we were trying to model. See how we can improve that model with this particular lecture. Okay. Now, first thing we need to talk about are quantities. First of all, you can have scalar quantities, which these are quantities that are fully described by magnitude or just like the numerical value just by themselves. So here's some examples. 55 grams, that'd be a good mass. Time would be like 20 minutes. Distance would be 20 meters. Speed would be 55 miles per hour. So those would be an example of scalar quantities, okay? Things that are just described, fully described as just the value itself, okay? So now, we can talk about a vector quantity, which these are quantities that are fully described by both a magnitude and a direction. So the example of this would be the term that we're going to talk about today, velocity. So velocity is about 55 miles per hour north. Okay, so that would be 55 miles per hour. Here is the magnitude, and then of course the direction north. Okay, so magnitude 55 miles per hour, the direction north. So that would be a vector type of quantity. We'll get into that a little bit further in a little bit. Okay, so now the biggest thing is, what is motion? Okay, and for the most part, motion is fairly simple. It's a process of moving relative to a position. So now, here's the first question. You're standing in one place and your friend walks by you. Are you moving relative to your friend? And more importantly, is your friend moving relative to you? Let's see how you guys did. Okay, let's answer the first one. Are you moving relative to your friend? You are. You are moving relative to your friend. And why is that? Well, we can look at it the same way. Your friend is also moving relative to you. How does that work? Okay, we'll get into that here in just a little bit. But why is that? Why are you also, since you're standing still, why are you moving relative to your friend, and your friend is also moving relative to you? It's a very interesting question. Now let's ask the same question. So let's ask it a different way. Is either of you moving relative to the Earth? Okay, I'll give you a second to think about that. And of course, the answer is you specifically are not moving relative to the Earth, but your friend is. Now, you are both moving relative to the sun. So that would be another way to think about that question. Okay, since you're standing still on the Earth, you are technically moving relative to the sun. Okay, let's ask another question. Okay, if you and your friend are walking down the hall together at the same speed in the same direction, are you moving relative to your friend? More importantly, is your friend moving relative to you? What's the obvious answer? Okay, you are not moving relative to your friend, and your friend is not moving relative to you. Again, why is that true? Okay, let's ask that one more time. Okay, again, you're walking down the hallway, same speed and same direction as your friend. Are either of you moving relative to the Earth? Now, if we look at that, you are both moving relative to the Earth. So what does this come up? We have several questions here. Okay, how are we determining whether we are moving or not? And here's the answer. We have to look at something called the reference point with awesome animation. Thank you, Mr. Osterman. Now, a reference point is a point used to find or describe the location of something. Okay, so it's that point, that fixed point, where we can say, okay, you are moving relative to that point. Okay, so motion is a change in position relative to that reference point. So if we go back and think about if you guys are walking out in the hallway at the same speed and direction, well, if my reference point is my friend next to me, I'm not changing my position based on her. We're moving at the same speed in the same direction. Now, if the reference point is the Earth below me and I move, well then yes, I have changed my position relative to that point. Okay, so now let's take a couple steps back and we'll talk about you standing still on the Earth and your friend is moving back and forth. Okay, Your friend moves past you. Your friend's motion is relative to you. So yes, they have changed positions. Okay. If we're looking at you specifically as a reference to them, okay, if you're basing your position relative to them, if they change, then yes, you still are changing your position because your reference point and you have changed. Okay, you have changed, you have increased your distance from your reference point. So therefore, even though you haven't moved, you are in fact moving relative to your reference point. So that's a big term, relative. Okay, it's one of those things where it's a relationship between you and something else. Okay, so thing we have to also talk about is the starting point, and this is the point at which an object begins to move relative to the reference point. Okay, so it'll end up being this is where your object is starting. Okay, so examples of that would be positive 4 meters. This is talking about in front of the reference point, or negative 4 meters, which is talking about behind the reference point. Okay. Other things that we need to discuss, of course, are distance, of course, along which someone or something moves relative to that reference point. Obvious cardinal directions that we can use are north, south, east, and west. In graphical motion, we can use positive and negative distance to talk about these things, but away from the reference point and toward the reference point. So we can use directions to kind of help us with our distance as well. Okay, so this is kind of where we got to with vector quantities, north, south, east, and west, and we'll use positive and negative when we talk about graphical motion or even motion map type of things. Okay, so displacement, another term, another key term. Displacement is the distance from the starting point. Okay, so we have a question here for you. If we're going to just talk about the distance from the starting point, okay, see if you can't solve this. A person walks from their house to the end of the block, which is 40 meters away. They begin to return to their house, but stop and talk to a kind neighbor, which is about 15 meters from the corner that they were at. Now, what is their displacement? I'll give you a second to think about it. 40 meters to the corner, 15 meters back. What should be their displacement? And of course, for those of you that think fast and think clearly, 25 meters. Okay, so this is the displacement from the starting point. How far from the starting point do they end up? Okay, so at the end of the motion, at the end of the time segment, how far from the starting point do they end up? That's a new term, displacement. Now, we talked about displacement, or we can talk about displacement when we talk about finding volume. And again, that was a change of initial position to final position. It's the same thing, the same idea. How far from the reference point? What's your final position? What was your initial position? Okay, and find the change in. So it doesn't really matter how far you've gone. The total distance here was obviously, if you look at total distance walked, it'd be 40 meters and 15 meters added together. It'd be 55 meters. Okay. Displacement is just simply talking about how far did you finally end up after you started. Okay. So if you started at 0 meters and you ended up at 25 meters, that's your displacement. Okay. So the displacement will be one of those terms that you guys have to kind of chew on a little bit and understand, but the idea is that it's really the final position minus the initial position. Okay. Of course, time, a period during which an action, process, or condition exists or continues. So examples of time would be like 25 seconds. Most of the things that we do in our lab will be in seconds because they'll occur very rapidly. Obviously, you can talk about I'll be there in 15 minutes, okay, or it'll take an hour for that casserole to bake. Those types of things are all times, okay? So now, how do we put all these things together? Well, we have this thing called speed. So when we're talking about motion, we have to be able to describe how fast, per se, something moves, okay? What's the rate? So speed is a rate, okay? Speed is really equal to the distance divided by time. It's a rate. It's the distance covered over time, okay? So this is kind of a visual for you as far as how you can get distance. If you take speed and times or divided by time, you can get distance and so on and so forth, or distance divided by time, you get speed and so on and so forth, okay? So, example, a car will travel at 300 kilometers in 6 hours. What is the speed of the car? Again, you guys talked about this last year. Distance divided by time would be 300. for the distance. 6 hours divided by is the time. So 300 divided by 6 gives you a grand total of 50 kilometers per hour. Okay, so fairly straightforward as far as how to find speed. Okay, so let's do a couple more practice problems. Okay. Okay, how far can a plane travel if it flies at 800 kilometers per hour for 9 hours? And also, how long does it take a ship to go 500 kilometers if it travels at a speed of 50 kilometers per hour? Go ahead and pause the video and see if you can't solve these two questions. Thank you to those of you that actually took the time to solve it. So number one, of course, if you take 800 and you divide it by 9, or times 9, excuse me, you should get 7,200 kilometers. So it gives you the speed, 800 kilometers per hour. Take it times 9, and you should get 7,200. Okay? Now, answer 2 should be 500 divided by 50, which gives us 10 hours. Okay? So, thank you for those of you that actually did that. So speed in a given direction is called the velocity. So what is the velocity of a boat that travels from St. Peter to Mankato, which is 10 miles in 15 minutes? And your answer, speed is equal to distance divided by time. Speed is equal to 10 miles divided by 15 minutes. This gives us 0.67 miles per minute. So now, if we want to, we can add the velocity. Since Mankato was south, okay, we can add 0.67 miles per minute. South is the direction, so that's kind of where we'll end up as far as velocity is concerned. Okay, now changing your answer to miles per hour is something that's kind of nice. Okay, obviously if it's if you're trying to get to miles per hour, if there's 60 minutes in 1 hour, just multiply that rate times the current rate that you have, which is 0.67 miles per minute times 60 minutes per hour, should give us a grand total of 40 miles per hour. Okay, so we're getting better, we're getting down towards the end here as far as initial information is concerned. Now, the next thing that we need to be concerned about is distance versus time graphs. Okay, these are the things that we're going to be putting together, and then we can actually get an algebraic equation from this. Distance is the y, time is the x. Okay, this is obviously the graphical acknowledgement of the data. Okay, so this is how we can look at it. Obviously, the distance is measured here, and the time is measured there. And this point right here, the 0, 0, is the reference point. Okay, so these distances are relative to this particular reference for distance, and this time is obviously referenced to this 0 time. Okay, so this is the point in which all motion is going to start. Okay, so this is the motion as it occurs from this reference point. Now, since the motion has a y-intercept at this point, this is also its starting point. Okay, so reference point and starting point in this graph show that they are the same. Okay, so let's see if you guys can't do a little graphing practice yourself. Okay, so on your paper, I've given you a graph paper. Go ahead and graph this particular set of data. Go ahead and pause the video and do that. Okay, your graph should end up slightly like this. Now, notice our reference point is still 0, 0. The reference point, the point at which all motion is figured from, is right here, 0, 0. Now, the starting point, the point from which all motion has started, the point in which the motion starts is right here. The y-intercept is 5. So the starting point and the reference point in this graph are not the same. They are not the same. So if we're going to go ahead and put together a mathematical relationship of this particular graph, we would need to, oh, I'm sorry, I need to talk about this. Was your graph a straight line? Okay, yes. Okay, if we go back here, obviously this is a straight line. Now this straight line is going to represent something a little bit grander as we go to acceleration. But as we look at straight lines here, we're obviously looking at the idea of a constant velocity. Okay, so it indicates constant speed. Constant speed is the object does not speed up, which increases its speed, or slow down, which decreases its speed. That means the acceleration is 0. We'll define acceleration a little bit more later. Okay, so if we want to give a mathematical relationship, we need to be talking about slope. Okay, so we need to find the slope of the graph. So finding the slope of your graph is important, and that will equal the velocity. This graph, okay, the slope of this graph will be velocity. So, whoops. Okay, so to find the slope, obviously we're going to take the rise over the run from the starting point. Okay, from the starting point. So that's also, if you want to look at it from a purely graphical standpoint, we're looking at the change in distance divided by the change in time. The rise, of course, was distances. The run, of course, was the times. So if we look at the change in distance over the change in time, we should be in good shape as far as finding slope. So in this particular, go ahead and find, or this time, excuse me, find the slope of your particular graph. And this is kind of what you should have found. It should have been about 2 meters per second. Again, the rise from here, and actually I did this particular graph wrong, I'm sorry. When we look at the rise, you're looking at a change in 20 over a change in 20. Actually, the slope is 1 meter per second. So I'd have to change that. So for those of you that found 1 meter per second, you're right. I took this particular number from the original graph and did not switch it. So we just have it up here. Okay, sorry about that. I didn't change my slope relative to my starting point when I was doing this. So it should be 1 meter per second. My apologies. All right, now distance versus time graphs are used to describe the motion of objects as shown in the graph. So here's another graph. You can see that we have an increase, then we have kind of a level off, and another increase all the way up here. So now a couple of things that we need to look at when we were looking at this picture, and some things that you probably need to mark out. Anytime you have something going or increasing its distance away from the reference point, you have positive motion. That's what the slope would be, is positive. So 100 meters divided by 4 seconds, okay, would give you a slope of, 15, no, not 15, 25. Sorry, 25 meters per second, okay? So now, that is a positive slope, so that means the motion is away from the reference point. Now, you'll notice this little flat line here. This little flat line that I'm circling with my cursor is not changing its distance. It's changing its time, but it's not changing its distance. So if we were to find the slope of that particular line, it would be 0 meters over 4 seconds, which is 0. So it's effectively stopped. The object is stopped when it flatlines. Okay. Then it just automatically begins moving again, and you can see we're using these 2 points here. 150 divided by 4 gives you somewhere right in the neighborhood of about 17 or 27, excuse me. 37 is the rough distance versus time of this particular line, so speed. Okay, so 37 right there. Okay, so we have some other directions here if you need to look at those. But it kind of shows you, again, no motion is here between 8 to 12. Okay? Okay, so then that's kind of where we'll stop. We'll pick up with acceleration next time. Thanks, kids.